Uh, so hello guys, let's wait for some time to see if somebody joins. That's a very good evening to you all. Today we'll be discussing some concepts and numerical problems from the current rate content, and then uh, we'll first start with discussing the assignment questions and solutions from last week. Okay. So let's wait for some time, then we'll start the session. Okay. So let's start with actually today's session. It is problem solving session 9. We are nearing to the end of this course actually. And today we'll be discussing assignment questions from last week. That is your assignment number 9. And then after that, we'll be taking up some of the concepts and then some problems, related problems from the current week content. Okay, that is your electro discharge machining process. I hope you have gone through this topic and all the videos of the current week. If it is so, then right now let's first start up with previous year's questions, assignment questions. Okay. So yeah, so this was your last week assignment. I hope all those questions were you could have done easily. And if you had any doubts or something, I hope that gets clarified now. To start with, the first question was which of the following is an assumption in MC-Shaw model? That during USM, ultrasonic machining process, we do some assumptions before we derive the MRR, right? Now, in that thing, we actually assume, as per MC-Shaw's model, that all the grains are identical and spherical in shape, actually. So these are not cubical. So the first option becomes wrong. And then the second option said the rate of work removal is not dependent on frequency. But actually the rate of work removal is dependent on frequency. If you have noticed, you have three particular things on which the MR are dependent. Those were the volume of material removed, the frequency, and then your number of particles impinging. Okay. So second option is also wrong. And then all the grains are not identical is not an assumption. All the grains are identical, that is assumed. So the fourth option is correct one. The rate of work removal is proportional to frequency, right? Then the second question asked for USM process, MRR is the proportionality of MRR, okay? So from the final expression, actually you can see that it is directly proportional to 3/4. The feed force raised to the power 0.75. Okay. Similarly, it was directly proportional to the amplitude with the same power, that is 0.75. It was directly proportional to the frequency of vibration, as we discussed in the question above. So all these options were correct in this question. And then in AJM, abrasive jet machining, material is removed by, so it is due to the impinging action of the abrasives, right? So metal evaporation is not the answer, and vibrational tool impinging abrasive grains on the workpiece, that is the cause, and the effect is brittle fracture due to that impingement, right? So third option is the correct here, and thermal breakdown doesn't happen in case of abrasive jet machining. So next question was, which of the following is true for iron milling? Okay. So in iron milling, you know that the impact energy happens to be low, right? Happens to be high, isn't it? So the third option here, the mean free path is comparable to chamber size. Okay, that is the correct option. And the light source is not used. Actually, the ion energy is used to abrade the substrate. So second option is also wrong. And the mean free path is comparable to chamber size. Yeah, that's the correct option. So the option C becomes your correct one in case of ion milling. Now the fifth question was about your ultrasonic machining. You just had to mark the points C, O, A, B with respect to your positions of the tool and your grain. Okay. So as the tool starts motion, so C becomes your initial position or the top position, right? And then A is when the tool touches the grain, and B is when the by how much the tool has entered into the grain. Okay, penetrated to the grain. So O is actually your mean position. Okay, so option C follows. I hope that's clear. Okay, so and the sixth question, it asked that in dry oxidation, what reacts with silicon, while in wet oxidation, what reacts with silicon at what temperature? So, you know, in dry oxidation, pure oxygen reacts, and in wet oxidation, water vapor actually reacts, and the temperature is, of course, high. So option B follows. And then the next question was for USM process. What should be the tool property? Yeah, ductile, brittle, hard or tough, or soft, what? And so as the tool is subjected to an oscillatory motion, to and fro motion, and the grains are usually hard, the abrasive grains are hard and ones, so the tool should be tough. Okay, the tool should be tough and ductile at the same time. So the next question was in AJM. How does MRR varies with respect to mixing ratio? Now, the mixing ratio of abrasives and your water. Okay. Now, the MRR, we had discussed that last session, how the MRR varied, isn't it? So ideally, it should have gone on increasing, but that doesn't happen because of crushing of your grains, and it initially increase and then happens to decrease after a particular optimal point. Okay, and then in case of hollow tool, that is a hollow tool, so what should be the thickness? Okay, so what should be the wall thickness? Okay, or you can if you take up from the options, so you can see that option A only matches the thickness per tool which are given and not the correct ones. So the wall thickness should be there and should be at least 0.5 to 0.8 millimeters. And the last question was, which of the following is not used as an abrasive in AGM process? Silicon carbide, aluminum oxide are of course used. Sapphire is never used in case of AGM process, okay, as an abrasive material. So because that would again add up to your cost. So why should we go for that? Aluminum oxide and silicon carbide are of course used. So option B is sapphire is not used in case of AGM process. Okay. So I hope you don't have any doubt in these questions. So if you don't have any doubts, we'll just move to some of the concepts. I will discuss some of the concepts and questions out of the EDM process. So let's share my screen for EDM process actually. So we will actually start with clearing your concept of the material removal mechanism in EDM. Okay. If your idea about the material removal process becomes clear, I hope that will make up your basis to solve any kind of questions out of this process. Okay. So what actually is the material removal process in EDM? So you know that happens due to melting and evaporation as a single word answer, right? Now, that is a very vague reply, and actually you have to think of what is the detailed process is. So you know there are two types of voltages. One is your supply voltage, and another is your discharge voltage. Okay? So you charge up the capacitor, and then once the discharge voltage or VD is reached, so what happens then? As your discharge voltage VD is reached, okay, the electrons, wait, before that, let's discuss about the circuit, what happens in case of EDM. So you have a tool which is connected to the negative terminal of the voltage source, and this is acts as a cathode. Okay, and the workpiece acts as your anode. Now, and this is a variable resistor. This is your supply voltage V0, and this is your capacitor for storing your charge. This is a tool which can be a brass or a copper, and then this is your workpiece. Okay. Now this is the way that how the gap voltage varies with your time constants. Okay. As the time increases, you can see a peak. Before a peak supply voltage is reached, we have another voltage called discharge voltage. Now, when the discharge voltage is reached, the electrons starts to accelerate toward your anode. Okay, so cathode is connected to negative terminal. You know it is full of negatively charged electrons. Electrons starts traveling towards your anode, and ion starts traveling towards your tool or cathode. Okay. Now, when the electron starts traveling, they start colliding with some other molecules of the dielectric medium. You know, the dielectric can be some kerosene, okay, or some hydrocarbon biomass things like petroleum, okay, petroleum oil. Now, these are full of their own molecules. Now, as the electron starts traveling towards the anode, it starts colliding with the molecules of the dielectric medium and then break them down to electrons and ions again. Okay. So what results is generation of an ionized column of dielectric fluid molecules. Okay. That goes on, the bulk goes on increasing in volume as the time constant increases. Okay, and then the two electrode once gets connected at a time when the ionized column is has a sufficient length to connect the two electrodes. Okay, so once the two electrodes gets connected, you can see an avalanche of electrons. Okay. An avalanche of electrons, right? A huge quantity of electrons traveling at a fast speed towards the anode from the cathode, and then that generates a spark. Okay. Now, the spark is characterized by high temperature, maybe in the order of 8,000 to 12,000 degrees centigrade even. And this high temperature then vaporizes your electrode materials, okay? Mostly your anode, the workpiece. So that starts by creation of small craters at the electrodes, okay? And that is how your workpiece gaps eroded and material removal takes place to get the desired shape of the material, okay? So if that is clear, I hope that is clear. So if that is clear, then let me ask one question, that why actually it is the thing that material removal is more from cathode than your anode. So actually the fact is that the momentum of electrons, the stream or avalanche of electrons is far higher than that of the ions. So subsequently, when a higher momentum of electron impinges on your cathode, the material removal is consequently higher from that part, from that electrode. That is one cause. There are more causes. One is pyrolysis of dielectric fluid. Okay, the pyrolysis actually gives rise to a thin layer of carbon on the cathode. And so that is called as pyrolytic carbon. So that that's the reason that and because of a layer, protective layer happens on the cathode. You can see the pyrolysis is the process of thermal decomposition of materials at elevated temperatures, often at inert atmosphere. So here it is actually your dielectric fluid, which you use during your EDM process. A carbon layer gets created, a thin layer of carbon gets created and gets deposited on the cathode surface. Okay, so consequently, your anode, which is actually your workpiece, doesn't have such a layer because that is positively charged, and hence what happens is your anodic erosion is much higher than your cathodic erosion. And there is one more reason, that a compressive force is developed on the cathode surface, and because of a larger volume of electrons impinging over the surface. And ions released from the anode, compressing or inserting a compressive force on the cathode surface. Okay, so all these factors finally leads to the fact that erosion is much higher than your anode as compared to your cathode surface. Okay, I hope that is clear. So having said that, let's look at the basic requirements of an ideal dielectric fluid. Okay, so what is the basic reason for using a dielectric in an EDM process or anywhere? Right, so dielectric generally has a capacity to store charges. Okay, now that means the dielectric should not have uh, uh, conductive nature chemically, or it should be a neutral one, first thing. Okay, and then secondly, it should not be that viscous that it resists the flow of charged particles through it. Okay, and then that means it should be least viscous. Okay, and then it should not be inflammable. uh, should not be inflammable. Then it should, of course, low cost, and is always is one of the most common parameters in any design things we do. And then toxic vapors should not be there, which interrupts uh, the evaporation process or the material removal process. So these are your primary characteristics of the dielectric fluid in case of EDM, which should be taken care of. Having said that, we'll then move to our next thing, is that if these are the requirements of a dielectric, then why can't we use water? Water actually has all these characteristics. Okay, so all these characteristics are present in water also. So why don't we directly go and use water as a dielectric medium? Yeah, correct. So good conductor of electricity, yeah, that is a primary factor actually. Now, mm, so that is one factor. There are some other factors which are rusting that is caused by water. Okay, so the water rust, the water use of water, usage of water is a dielectric, leads to rusting on the pigments as well as the electrode surfaces, and that leads to deterioration of the electrodes. Okay, and then actually the conductivity of water, what happens is that the electrodes are always under potential difference. Okay, one is connected to the positive terminal, another is connected to the negative terminal. Now if we use water, it causes distortion of the workpiece, isn't it? And of course that also leads to a power wastage, and finally adds up to your cost of the manufacturing process or the EDM process, isn't it? So that's why we can't use water, and the mostly used dielectrics are if you have heard already, are your kerosene, okay, or any hydrocarbon oils. Okay, so I hope the initial some small concepts have been clear to you by now. If it is so, let me ask you one question. How to find out the volume of crater formed during EDM? You know, we have already discussed earlier Okay, that the process actually starts by creation of small craters, right? And and these are formed due to the material removals. Now, how do you estimate that what is the volume of crater formed, or how much is the volume of material removed we can actually gauge from the volume of the formed crater, right? Now, so give it a try. There are some hints given to you in the screen. So taking up, so this you can imagine as a crater. Okay, this you can imagine as a crater, and this is your crater. Okay, and then this is your depth. Okay, HC, which is shown here, is the depth of the crater formed. A is the radius of your crater, assuming that it is a spherical crater. Okay, it is not necessary that the crater will be spherical, though. However, for the ease of calculation, let's assume that it is a spherical crater. Now, in that case, A is your radius of the particular crater, and R is the radius of the sphere, entire sphere that it embodies. Okay, this is a part of that sphere, and R is the radius of that particular sphere that it embodies. Now, taking that up, can you determine what is the volume of the crater formed? You give it a try, and then we'll discuss it. Actually, it is pretty much straightforward here onwards. So you go on finding the value of your height, okay, at point A and B, and then you can integrate from A to B what much is the volume taken up. Okay, so give it a try. Okay, so if we continue with the discussion to determine or derive the crater volume, so if we assume a crater formed and the sphere, it is a part of its radius r, as you can see in the diagram, and then let A be the radius of this particular crater, and then it's be the depth of the crater. Okay. Then using Pythagoras, you can see a simple Pythagoras. You can see that the whole this is R, right? Now from here to here, it is that is also R. Now R, what is this portion? What is this portion? This is if this whole thing is your R, and this part is your HC, then how much this becomes? This is R minus HC, right? So R minus HC square plus this radius S square gives your hypotenuse, which is R, okay, R square. So you just break it down, R square plus HC square minus 2R of HC, okay. So then plus S square is your R square, okay. So you just rearrange the terms to get 2RHC minus HC square equal to A square. And from that, you derive that R is your A square plus HC square by twice of HC, okay? So if you refer to this diagram, how much is the height up to point A? It is R minus HC, isn't it? So A is your R, the total radius, minus of HC. Okay, and here you can see that at point A, R minus, sorry, that is HC actually. So yeah, that is HC. And then if you just plug it in here, you can find that R minus HC is equal to A square minus HC square by twice of HC. And then you find the same thing at point B, okay? So it is simply R. So whatever you have found out here, the value of R, you plug in here at point B. That is A square plus HC square by twice of HC. If that is done, you proceed to find the volume through volume integral, okay? From mathematics, undergrad mathematics, you must be knowing how to find the volume of a crater. Let us suppose this is a strip, okay, and this shaded portion, this is a strip of radius A. We have, what have we done? We have just inverted this particular we have just inverted this particular crater, okay, just invert it bottom up. So then you see this type of structure, and this is the entire circular or spherical crater which might have formed, of which this is a part, okay. And then you just find out a strip and just integrate it from A to B, the entire height, okay. If your directions are given by X in the horizontal direction and Y in the vertical direction, then with a differential length dy, you just integrate the volume, okay. So pi A square is the area of this particular circle shaded in black, and the dy, let's suppose, is a differential height, okay. Dy be the differential thickness, okay. So once you have done that, you just integrate it from point A to B and to find out the crater volume, okay. It's pretty simple. Now A and B we have found out earlier as A square minus H square by 2HC once, A square plus H square by 2HC in the second case. Okay, so you plug in the values and just integrate it, you replace a in terms of y. Okay, so that becomes r square, okay, minus of y square. Okay, let this be y. Okay, so s by Pythagoras again. So a is root over of r square minus y square. Then your a square becomes simple r square minus y square. Done. So if that is given, you just integrate it from a to b to find out. Okay, so this is the step of integration, intermediate step being shown. You find out that your VC is actually pi by 6 of h. H is your crater height or crater depth, size of a square your crater radius, and h is again your crater depth. So you one variable, which is the radius of on the spherical total sphere out of which the crater is a part, is done. Okay? So now you know, if you are given, if you can find out somehow crater depth, okay, and radius, you can find out the volume of material removed out of the crater, assuming it is a spherical one. And if that is found, I hope somebody's mic is on. If you can switch it off. So the crater height is proportional to z. Okay, so let z be the actual depth of the crater formed, and it is an instantaneous height. Okay, we have assumed it, and the total depth is z. Now, if you can find out, so h is proportional to z. Okay, it is in the same direction, isn't it? If this be your crater, this be your hc. Okay. Now, if whatever dimension of crater being formed, z be the total depth, then z is an indication of material removal by its part. Okay, so very simple. So proceeding, what we see is so. What we see here is that this is one empirical relation. Okay, this is one empirical relation which has been found experimentally. Okay, that hc is actually proportional to some constant k1 and w, which is nothing but your spark energy. Okay, in joule. So the net dimension of depth here, the unit is centimeters. And again, a, the radius of your crater is actually constant k2 again, and w, your spark energy raised to the power 1 by 3, okay, divided by 2, half of that, that gives your a. Now you just plug in the values, the empirical values of hc and twice of hc and a in your crater volume formula, which have been derived right now, to find out the total crater volume in terms of your empirical constants k1 and your spark energy w as this one. Okay, pi by 6 k1 into 3 by 4 k2 square plus k1 square whole of multiplied by w. Okay, here you can take up the constants k. Actually, these have been found out, and I have shown here for your idea, like let you know what type of values can these be. These are for copper. Okay, it is 0.4 and 0.045. Has been empirically found out, okay, during electrolytic machining of copper. So yeah, that pretty much concludes this topic. So we'll move up to some numericals here on. I hope after this it is clear to you. Okay, so let's move ahead. Mm, we have a numerical now to solve, and this is simply based on your RC relaxation circuit during EDM process. Okay? This is RC type generator, and the maximum charging voltage is 80 volts, and charging capacitor is 100 microfarad. Okay. Now you have to determine the spark energy. So it is pretty simple. Here you have this term becoming zero because your TD or discharge time is almost equal to zero. And so the spark energy becomes half C of your charging or discharge voltage VD square. Okay. So if that is so, your capacitance value C is given, and then your voltage VD is or VC here. You can see the same thing. 80 volts is given. So you just plug in the values and find out the energy is 0.32 joule. Okay. Hope that's clear. So it's a simple problem, direct formula based. If you have got it, then we'll proceed to find out a more detailed problem afterwards in the upcoming slides. Okay, so let's proceed. This is one more question. Here you can see that for an RC type generator to get maximum power dissipation during charging, VC is given as 0.716 V naught, or you can we have derived that in your class that VC or VD, you can say here it is almost equal to 72% of V naught. Your V naught is your supply voltage, right? Now, if that is given, and ideal, you have to determine the ideal time for RC as 10 ohms and capacitance is 200 UF. Okay. So you just plug in into the equations. You know TC. You know the equation of TC is given by your RC natural log of V naught by V naught minus VD, or as we see here. Okay, that's the same thing. And then just this has been rearranged to just look up like that. So you just plug in the values. Only TC is unknown in this equation. You know the capacitance value as 200 microfarads. You know the resistance value as 10 ohms, and it is given that your VC or VD here is 0.72 or 72% of V naught. You just plug in the values and find out your TCS to 517.56 microseconds, or you can say 2.517 milliseconds. Okay. So it is almost similar to our last question. If you have got it, we'll proceed to one or two more questions. Okay, let's proceed to the next question. It is a resistance capacitance relaxation circuit is used in EGM process. The discharge voltage is given to you as 100 volts and at a spark cycle time of 25 microseconds. The average power input is given as 1 kilowatt. The capacitance in the circuit has to be found out. Okay, this question arrived in your gate set 2, 2015. And this is a pretty simple question. Um, if you have got the earlier two questions, then it is also kind of that only. So again, this part is 0. Okay, so it becomes e to the power 0 is 1, and then only energy, spark energy is contains your half c d square. So you just plug in the values. Okay, C is given. Okay, C is has to be found out, and the power input is given as 1 kilowatts. Okay, and then C has to be found out, and voltage is given as 100 volts. Okay. Now the spark cycle time is 25 meters, so the total power then becomes this joules. Okay, you know what is the unit of your power, and that is joule per second. So you have to find out the total power to total energy, that is multiplying power by time to find out this. To plug in the value in this equation, and from that solving this equation, you find out that your capacitance is nothing but 5 microfarads. Okay, so only one twist here was to find out the value of total energy. Okay, just take a note that you shouldn't put in the value of power in case of energy here. Okay, so 1 kilowatt will give you a wrong answer. Okay, you should find the energy as your power multiplied by time in seconds. Okay. So given that, we'll proceed. Okay. So next question. So this question is a little detailed one, and it asks that during an electrodischarge drilling, okay, the principle is similar to electrodischarge machining. Okay, it is just a type of electrodischarge machining. So it says that during EDM or electrodischarge drilling of a 10 square hole in a low carbon workpiece is a steel plate. Now a brass tool and is used as a tool, and the kerosene is used as your dielectric. So given those things, the resistance and capacitance of the relaxation circuit are 50 ohms and 10 microfarads. The supply voltage is 200 volts, and the gap is maintained so that discharge takes place at 150 volts. You have to estimate the time required to complete the operation. So you give it a try, and then we'll discuss the solution. Okay. Yeah, so this question, we had to find the time required to complete the operation. Now, a similar concept we had discussed in earlier sessions. In that case, you have to find out the volume of material that is needed to be removed, okay? And then you divide that by your material removal rate. If you check the units, your volume removed shall be in millimeter cubes, and your material removal rate shall be in millimeter cubes per unit time. Now, if when you divide your volume by your removal rate, you finally find out the time of machining, okay? Now, in this question, you have been given an electrodischarge drilling operation. You have a steel plate. So what does that mean? Is that you can use the empirical relationship to determine your Q material removal rate, which is your 27.4 into your W to the power 1.54, okay, where your W is the power, okay, which is found out by dividing the energy of uh, spark by your cycle time Tc. Okay, so let's look at the solution. Then you can see here that you first find out the energy amount of energy released per spark. Okay, that is half cvd square, as we have done in the previous problems. Right now, once you have found that, you just divide that by your cycle time Tc, which is your RC log V naught by V naught minus Vd. V naught is your supply voltage and Vd is your discharge voltage. R is your resistance and C is your capacitance value. All these values has been given to you. You just plug in the values and you find out your energy and cycle time. Okay, energy comes out to 0.11 joule, and cycle time comes out to be almost equal to 7 into 10 to the power minus 4 seconds, or you can say 0.7 milliseconds, right? Now, proceeding, you have to find out the average power input, which we just mentioned. Now, that is given by your energy per unit cycle time, okay? You just divide that, you find out that your average power input is almost equal to 0.16 kilowatts. And now, since the workpiece is made up of steel, we can use the empirical relationship of determining MRR. That relationship is 27.4. Okay, into power input, average power input in kilowatts. You should remember that this W is always in kilowatts. You should not plug in the value in watts. Okay? So you just plug in the average power input. We have found out as 0.16 kilowatts here, raised to the power 1.54, and we find out the Q as 1.63 millimeter cubes per minute. Okay, given that your total volume of material, you have been given the plate dimension as 5 millimeter thickness, and your square hole has to be inscribed, okay, and it is 10 mm side square hole. So that is, let us assume that is equal to the volume of material removed, area of the net volume to be removed. So you have 10 cross 10 cross 5 as the net volume to be removed, and that gives up your total volume to be removed as 500 cubes. Okay, now you just divide your total volume in cube by material removal rate in cube per minute to get the total time as almost equal to 306 minutes. Okay? So that answers your question. I hope that's clear to you all. If you have any doubts regarding this question, please put up. So it is clear to everyone, right? No doubts, no questions. So then, if not, then this is last topic probably of today's session. It says, what is the role of cavitation in EDM? Okay. Now, first of all, do you know what's cavitation actually? So cavitation is a phenomenon which happens when the pressure is falls much lower. Okay, so let's suppose in case of a turbofans or a jet engine. Okay, so what happens, or propeller? Okay, what happens is it's rotating at very high speeds, right? So when it rotates at very high speeds, often the pressure falls much below, often below the atmospheric pressure also. And as a result of which, and the solution or the fluid in which it is in touch with, maybe air, maybe some water in case of a propeller. So what happens is your some bubbles gets formed, okay, because it starts boiling at much lower pressures. It starts boiling at lower temperatures itself. So some bubbles gets formed, and when these bubbles burst, it erodes the material to which it is in touch with. Okay, so that particular phenomenon is called as your cavitation. So the same happens in case of EDM also. When the pressure falls much below atmospheric, the cavitation process takes place and the bubbles burst, and then your MRR, and that affects, adds up to your material removal. Okay, because beside your actual MRR which is taking place in the presence of a dielectric, the cavitation process further leads to erosion of the electrode surfaces, okay, and removal or erosion of material from the electrode. So overall, what it is seen is that due to cavitation phenomenon taking place, the MRR becomes maximum during a spark cycle Q when the pressure falls below atmospheric pressure. Okay, when the working pressure falls below atmospheric pressure. So that is one interesting phenomenon which happens in EDM, and you all should know that. So yeah, so that pretty much concludes today's session. Now you can shoot your questions if you have any, and I'll be happy to discuss with you all. Okay.